Hi, we want to explore the sampling of continuous time sinusoids. Our continuous time sinusoid is going to be here, and what we want to do is produce the discrete sampled input data here. We're going to start off with a project requirement or a hypothesis that we're going to find this pattern in the input. What we have to do is translate this pattern into a sampling interval that helps us sample right here where this arrow is. This is the sampling equation, and it's going to give us the slowest sampling interval that will give us one cycle of data. So when we look at it right here and we choose a sampling interval of 3, we can see 1, 2, 3, 4, 5 samples of data within one cycle. Then we see the exact same thing repeated. Now if we go below 3, everything works. Of course, a faster sampling rate is better. But the question is, suppose we have data from somebody else. We didn't get to choose a sampling interval. Are there sampling intervals slower than 3 that work? Here's 5. And that gives us 1, 2, 3 bits of data to reconstruct the sinusoid. And you can see that we're getting closer and closer to not being able to have confidence in this pattern. If we look at 7.5, that's giving us 2 samples per cycle. If we look at 15, that's giving us 1 sample per cycle. So clearly 3 is what gives us the minimum number of samples per cycle to actually be confident that we can reproduce that sinusoid. Now this question is to get you to start thinking in terms of a slower sampling per second. And you can notice a straight line at 15 and another at 30. But you see how this 30 skips a cycle. But when we take that data and put it right next to that data in a column in a spreadsheet, this distance doesn't matter. What does matter is that the actual input, the actual microphone linear sensor, the transducer, is repeating itself. Here we see the 7.5 millisecond pattern repeating itself in that positive, negative pattern, and then we can move it up to 22.5, and we see it positive, negative, going on and on and on. So the question is, why are we looking at this stuff? Well, there are examples of that pattern existing, and we can get hints and say, yeah, maybe it's there if we have data that was sampled much slower than we need. Up here we predict that phase has no impact on the data that we collect. So here we're manipulating the phase, and you can see that we can still find that pattern. Maybe its magnitude changes a bit. We'd have to go into the algorithm of how the magnitude's computed. But phase really isn't impacting things. If there's many repeating identical cycles in the input, then we can skip around while sampling. This illustrates that. Here I've got a sampling rate of 3 milliseconds, and you can see I have 2 highs and 3 lows. And if I switch to 18 milliseconds sampling, I get the exact same data. So the blue dots represent numbers in a column in a spreadsheet, and we're getting the exact same numbers as we get right here, but we've got a sampling rate of 18 milliseconds. So we can dig information out of data that wasn't sampled fast enough. We're all familiar with the Wagon-Wheel Effect, where the tire in the car appears to be spinning in the opposite direction of the car. This is a negative sampling rate concept. It all starts with just this identity that you memorized in trig classes. So let's just first explore this identity. So what I have here is a sampling rate of 3 milliseconds, and we're just going to switch between a sampling rate of negative 3 milliseconds and positive 3 milliseconds. And you can see there's no difference. But you say there's no such thing as negative time, and negative 3 milliseconds makes no sense. But when you add a circle to that, when you add skipping cycles to that, then you get something positive. You get a first negative sampling rate of 12 milliseconds and then 27 milliseconds. So let's check that out. So here we go. Here's 3. And you can see the pattern's the same. Now we're going to go to 12. It's reversed. Then we go to 18. Remember, that's positive. Same thing. Then we go to low. And we go high, high, low, low, low. It's almost as if the negative sampling rates reverse time. But we're not looking at time here. We're just looking at a series of numbers in a column on a spreadsheet. But the concept of negative sampling helped us find other patterns in the data. But the wagon-wheel effect we see with our eyes. So it's not just a concept. Our brains, our eyes, are somehow sampling the data, and that's us experiencing a negative frequency. But wait a sec, cosine of a negative theta equals cosine of theta. And we didn't see that reversal of time. Well, what's causing this backwards and forwards of time once we start adding the 2 pi? Let's zero out our phase, and all of a sudden, repeating with the same 4 frequencies, we get the exact same pattern. It says double down. You see the double down, double down. Man, this is fascinating. It should force you to stop right here, sleep on it, dream about it, and come up the next morning and start telling yourself stories about this.